To wrap up our astrophysics topic, we are going to look at the beginning, the Big Bang, and the end, what we think the universe is ultimately going to do. In order to get us there, we need to zoom back out and talk about all the different stellar properties and how we can calculate for them, to ultimately turn into what we call the cosmic ladder, ways of calculating how far away something is and deeper into space. So, to reintroduce and review what we have. There are three main sections for the IB physics curriculum. It is stellar quantities, where we have some properties for stars like distance and parsecs, luminosity and brightness. Stellar characteristics, where we talked about how temperature can give us a wavelength and vice versa. And cosmology, some conversations and discussions about the universe, how the universe is changing and stretching and ultimately expanding. There are also some important properties that are constants, some unit conversions that we talked about, these astronomical quantities, and of course, the speed of light in a vacuum. Now, when we are measuring the universe, we often think of the universe when we look at it, it looks like a flat picture. But the reality is, it is not a flat picture. And of course, that sounds obvious. That, of course, is not flat. We know that space is this three-dimensional thing. But the stars that we see next to each other, even constellations that we are familiar with, like the Big Dipper and Orion, those stars in our night sky aren't actually physically close to each other. They might be many, many light years away from each other in that same constellation. So, how do we know that one star is close to us and one star is farther away? And what different ways can we use to determine exactly what that distance is? Well, this is where that cosmic ladder comes in. Each rung of this cosmic ladder allows us to go deeper and deeper into space. Our first level is the closest stars. These are the stars that move in the night sky when we are looking at them between like 6 month spans. And that difference in perspective makes it jump, kind of like your thumb would jump back and forth if you're changing which eye you're looking out of. And of course, we use that angle in parsecs or angle in arc seconds to calculate distance in parsecs and then convert that into light years and ultimately meters. Now, if we go a little bit farther out, we're not able to use parsecs anymore because this parallax angle is not going to help us uh, figure out a difference. We're not going to see it jump back and forth enough. So we have to use something like Cepheid variables, these stars that get brighter and dimmer in these set periods, like 5.4 days. And we look at what that period is on this luminosity period measurement from Henrietta Leavitt and use that to determine the luminosity of the star. This is called the standard candle strategy. And that standard candle, if we know the luminosity of that star and we know the brightness that we see it in the night sky, we can calculate the distance. So luminosity and brightness are enough to find distance. So we can measure a distance a little bit farther than parallax is able to do it. We can go a little bit further and look at just the color of the light that that star is emitting. The maximum wavelength is going to correspond to the temperature of that. And we know the HR diagram that most stars show up in the main sequence. So if I know the temperature, I can find what star in the main sequence roughly would result in that kind of temperature, and then what would its corresponding luminosity be. And again, if I know luminosity and I can see its brightness here on Earth, I can determine how far away that star is. Now, the last piece, these are for really, really far away stars or ultimately galaxies. We look at how the light is shifting. We know that certain elements exist in these stars and these galaxies, like helium and hydrogen, and we can look to see the signature, what frequencies and wavelengths we are expecting to see, and see how that has been shifted towards the red end of the spectrum. The amount that that is shifted or change in the wavelength is ultimately able to give us a velocity, how fast that universe or that galaxy is moving. And if I know how fast the galaxy is moving, I can determine what its distance is in megaparsecs and then convert from megaparsecs into meters and figure out a distance there as well. This comes from Edwin Hubble in discovering that the farther away something is, the faster it is moving. So if I know how fast it's moving, I know how far away it is. I can use that to help me get a distance. So this is a cosmological ladder, the cosmic ladder, helping us go farther and farther out into space and measure these distances. So, how old is the universe? If we're trying to figure out where it all began, we need to know when it all began. Well, this Hubble information, Hubble's constant of roughly 70 kilometers per second per megaparsec, tells us the relationship between the distance and its recessional velocity. But we can do something clever with this particular constant. We know that velocity is just distance divided by time. And if this is equal to velocity, HO, Hubble's constant, times d is equal to distance over time. Well, distance shows up on both sides, and I can cancel that out, which means HO is equal to 1 over t, or t, time, is equal to 1 over HO. Well, what is this time? This is the time that if you were to trace all of the expansion back, it predicts that it starts in one small place, and all must have began and converged at one point in time. This is that time. 1 divided by Hubble's constant is the age of the universe. Well, you might be saying, 1 divided by 70, how is that the age of anything? That's 0.0142. Well, the units here aren't in a unit of time that we are familiar with. It is seconds times megaparsecs divided by kilometers. What does that even mean? That doesn't sound like a time. Well, it's actually a time times a distance divided by a distance. So if I can do some fancy dimensional analysis, we can get those distances to get rid of each other and then ultimately be left with just a time. So let's display this in a little bit more dimensional analysis friendly strategy. Here I've got 0.0142 seconds times megaparsecs divided by kilometers. I want to get these distances to equal each other because if they are the same thing on the top and the bottom, they will cancel. So let's start with megaparsecs. Megaparsec is just a million parsecs, or 10 to the sixth parsecs. Are my megaparsecs cancel? And I have parsecs on top, kilometers on bottom. Still doesn't cancel. Now, parsecs are related to light years. 1 parsec is 3.26 light years. That cancels out. Then 1 light year is equal to 1 or 9.46 times 10 to the 15th meters. Light years cancel out. So now I have meters on top and kilometers on bottom. Really close. I know that there are 1,000 meters in 1 kilometer. The meters on bottom, so that those can cancel. Now I have kilometers on top, kilometers on bottom, they cancel too. So I'm left with just seconds. If I carry that all the way through, I get 4.4 times 10 to the 17th seconds. It's a lot of seconds. It's equal to about 13.8 billion years. This is our best approximation for roughly how old the universe is. Now, the trick here is Hubble's constant, this approximately 70, it changes depending on how you are choosing to measure it. And certain scientists that are measuring it in different ways sometimes converge at different values. There's one group of scientists that are saying that that's closer to 68, and one group of scientists that's saying that's closer to 72. And because of this, that changes our estimate of how long the universe has been around, because that number is one of the ways that we can determine the age of everything. Okay, so if the universe started somewhere 13.8 billion years ago, um, what did it start with? Well, you've probably heard of the term the Big Bang. This at one point was a controversial term. It was actually created by somebody who didn't believe that the universe started in this way and wanted to give it a name that people wouldn't believe as a scientifically valid or something that should be believed. So he called it the Big Bang. Uh, and that the name kind of stuck. So the Big Bang all starts with a very, very rapid inflation. This is a tiny fraction of a second, where the universe starts expanding into nothing. Very, very quickly, that inflation starts to give rise to the quark era, where quarks first start becoming uh, visible, and part of the energy gets converted into that matter. And those quarks can start to form into things like protons and neutrons. The natural laws form in still a tiny fraction of a second. This is less than a billionth of 1 second, that these natural laws that we are familiar with start to form, and then create hadrons and leptons. So this is when matter as we know it, uh, these subatomic particles start to form, things like protons and neutrons and electrons. Um, then those protons and neutrons, at about 1 second, start to form the first atoms. Most of these atoms are hydrogen atoms. They will then ultimately fuse to create things like helium, and then in the belly of stars, other things larger than that. And then the opaque era, about 200 seconds in, um, and ultimately the universe today was a pretty big jump there. We weren't able, when I say we, uh, things in the universe, light was not able to travel through for a long period of time. Things were too hot. It was opaque. It was basically this big orange soup that light is trapped by the electrons, and it isn't not until about 300,000 years in, which is still pretty early in the span of our cosmic scale, that light first gets to travel beyond. Now, how do we know that this is a thing? Well, it starts as just a theory of a way to describe how ultimately this expansion can have started somewhere. So if something's expanding, it must have expanded from something. And there was this quest to find evidence for a really long time, and it was kind of eluding scientists. Along come these two scientists for Bell Labs, Penzias and Wilson, and they were just doing some research on microwave radiation, and they had this really nice antenna that they were trying to find uh, this source of noise that was always there in their antenna. They thought it was something wrong with the antenna itself, and they worked on this for a long time. Ultimately, they published this paper saying like we can't locate what this noise is, and the scientists that were searching for the Big Bang said, "We know what that noise is. That is evidence that we've been looking for of this Big Bang." If it were to happen, there was a lot of energy remaining, and that energy dissipates over time and cools down. But we should still be able to see the light this that was emitted, kind of in that first stage when the universe first became transparent to light and allowed light to move. We call this the cosmic microwave background radiation, or the CMB. The microwave comes from the wavelength of this light is in the microwave part of the electromagnetic spectrum, and we see it everywhere. This is actually a three-dimensional picture. If we were to map it all out onto one oval, what we see. And you can see that there are some areas that are a little denser than others. Those are where stars and galaxies first formed. It is not perfectly even all the way through. Now, this cosmic microwave background radiation has a black body radiation curve, similar to other curves that we've seen for stars and other things that are glowing. And the peak frequency or the peak wavelength here is about 1 millimeter. This means that the universe has a temperature. Space has a temperature. We know that the temperature is so 1 millimeter or 0.001 meters can be plugged into this equation, the 2.9 times 10 to the negative third, divide by the max wavelength to get a temperature.
Meet the sheet. Toss the sheet.
This temperature, sorry,
Outer space looks blank.
video really wanted to start playing. This temperature can be found and calculated. Here we are seeing that it is about 2.9 Kelvin. So a little bit less than 3 Kelvin is the temperature of our universe. All right, so what's next? There have been many competing theories of what is to come next. For a long time, scientists, including Einstein, were convinced that our universe was static and infinite. It was infinitely large and unchanging. We obviously have some reason now to believe that that is not the case. We see these galaxies that are receding away from us, showing that the universe must be expanding. So we've kind of done away with that theory. Then there was a while where the belief was that it was expanding but slowing to a stop. The universe is made out of a lot of things that have mass, and things that have mass are gravitationally attracted to each other, which means that the thing that's on the outside should be being pulled in and slowed down to ultimately come to this either steady state or option three, where it expands, slows down, and then reverses course to lead to what was called the Big Crunch theory, and ultimately just kind of reverts itself and then kind of end where it started in one infinitely small point. We now, with our most recent technology, have seen that galaxies on the outermost edges of the universe are moving faster than we actually expect them to. And this Hubble's constant slope isn't really a straight line anymore. And we see that it is both expanding, but also accelerating. So not only is it getting bigger, it's getting bigger faster and faster as the universe continues on, which is a surprising result. We don't know where this energy is coming from to cause the universe expansion to accelerate. So we call it dark energy. And this is one of the biggest mysteries in science right now. It's what is dark energy and can we see it? Can we quantify it? And where is it coming from? But as far as we know right now, our most common theory currently is that the universe is both expanding and accelerating.